Yeah, so this is graph neural networks. And I make it a while ago, by the way. So why do we need graph neural networks compared to the regular neural networks, right? So the first thing is there's some data that's in graph structure, and the characteristics of the graph structure data is that we don't have a fixed input. So the input for neural networks pretty much has to be fixed, and if you want to increase the number of input, you have to change it to like recurrent neural networks. But in this case, if it's also another option is you can do graph structure data. Let me turn off my Discord. Okay. And then another one is if you want to know the relationship between the nodes. So for neural networks, you only care about like the input and the output. But for this case, you want to know what's the relationship between the nodes, but not just the input and output. And then it's also more efficient when you increase the graph size. If you convert this into neural network, it's still possible. But then when you increase the size, it's going to be more complicated and it's not as efficient if you use the graph size originally. And the last one is it's less sensitive to noise and outlier. So that's another one why we used to use graph neural networks in some case. When you have an outlier in a graph, the neural network's not going to respond as efficient, as good as the graph neural networks. And here's some application of graph neural networks. So this one is pretty famous. I think it's the one that bring up the graph neural networks that make this networks like famous. It's in drug and vaccine, and they go successfully to make a vaccine for a disease that actually works for graph neural networks. So that's pretty cool. And this one I think is OCAM, but you can like rearrange with this atom and this bond. And like the relationship between the node is important to the bond between the atoms. And then somehow they can use graph neural networks to understand them and make them create a molecular structure that can like solve the disease. And the other one is recommended system. So I don't exactly know how, but like you can just match the concept in a graph, and then you can make a ranking out of them, and you can have a recommendation system for people like YouTube and things like that. And here you have a fraud detection. This is from a paper, uh, fraud detection using graph neural network. I don't exactly know how it works, but like I saw the paper, so it probably works. Other things. So if you have like a graph kind of data, you can easily use convert this in this case as a map. So you can forecast traffic. So Google Map or Apple Map, you can use graph neural networks to predict the data on the map. You also have image processors. Actually this is used in neural networks, specifically convolution neural networks. But you can also use graph neural networks because if you think about it, each pixel is one node. And so you have this, but it's also a graph. It's just a special graph that all the node, they are ordered in a special order, and they are in order, and they're not just in other ways. So this is a special kind of graph. And also you have this over here is the social network analysis. So you have different pupil and relationship between pupil, and each person have a unique relationship, and they have like gender, nationality, location. This is pretty complicated. You can like match them. I know one of the application of them is to find like a date or something, like potential partner on the dating app. That's one of the thing. And
Sure, I
here's
have a few
some,
questions.
yes.
So, when I don't know if you're going to cover this later, but when I'm looking into these, I'm trying to understand how they update. So we have the nodes, and then we
Mhm.
have the links, right?
Mhm. The node and the link. Yes.
So is this kind of like in a neural network how each node is a function of the values of all the other nodes, and each
Uh,
link is a
mhm.
linear function?
Yeah, yes, exactly.
Okay. Um, each cycle is that the node gets data by the values of its neighbors, right?
Yeah.
And so
Yes.
and so maybe if we have like the largest degrees of separation is like six, maybe there's
Mhm.
going to be six iterations per cycle, right?
Like iteration per cycle. What do
Like
you
if
mean?
the furthest nodes from each other are have 6 degrees of separation, we're going to have to iterate 6 times per cycle,
Six
right?
down per cycle.
Because you have to you have to update each node by its neighbors, and then we update those neighbors by their neighbors, and then we
Oh
update
yeah.
those
Uh-huh.
neighbors by their,
Oh yeah, yeah, yeah.
and
Exactly. Uh-huh.
have to wait till it goes through a full circle, and that's a full cycle, right?
Uh-huh.
Okay, so it's almost like the graph is representing a hidden layer, but the hidden layers are all kinds of themselves. Each time it's the same. I'm sorry if this isn't making sense.
No,
So,
that's a good connection, yeah, between neural
okay,
networks
so
and GNN.
with neural networks, obviously we train it by like holding the nodes. Okay, so I understand how the nodes are updated by the values of the edges. The edges are linear functions, right?
Linear combination. And actually not linear because you have the activation function.
Sure. Okay, fair enough. But they're functions, right?
Mhm.
Um, how do we update those functions? Because I remember sometimes that you could actually change the values of the edges. Um, how like is it like a loss function? Like how do we? You could I covered this later, but like how would we train it,
Let's see. Like train a
or do we not
function.
work differently?
Right. I mean, I don't really know.
Okay.
Probably,
All
we
right.
probably get there when I do the math of this. We can get deeper in there.
Okay. All right.
Yeah.
Fair enough.
Mhm. So this is vocabulary. You probably knew already, or if you don't know, time to learn. This is called the node. So we have a different node. And then between the node, you have the edge. It's called the edge. If you connect two nodes. And for edge, you can have two type. You can have directed edge or you have undirected edge. So for directed edge, you go from one node to the other. It's one way only. You cannot go the other way. It's only one way. But for undirected edge, you can go either way. So one node to the other node and the other way. So both of them works. And then a graph, definition of graph is just a combination of different nodes and edge. And this whole thing is called a graph. So what can graph neural networks predict? So based on the vocabulary we know before, we can predict either the node of it. So you have all the node and you have a new node. So you want to predict what's this node about. And so you can predict the edge of the graph. So that's one. And then the last one is the whole graph on the level. So you can see you have a node, edge, and graph. So same here, you can predict the node, you can predict the edge, and you can predict the whole graph. So again, this another vocabulary. Just recap, you have the node here, and then you have, this is called a directed edge. You go from this node to this node. You cannot go the other way around. Now, so there's a new vocabulary, it's called embedding. So if one node is described by vectors of numbers or state, state vector actually, and this state vector, this embedding is going to describe whatever this node is. It's like a numerical description of the node. Then here you have, let's see, that. So down here you have aggregate, aggregate, yeah. So the act of aggregate is when you combine the neighboring nodes. So you have this yellow node here. If you aggregate, which means that you take the information from this blue node, you take information from this blue node, you take information from this blue node, so all the neighboring nodes of this yellow node, and you combine them all, and that's called aggregate. And this is, the next one is going to be message passing. So by message passing is pretty much mean aggregate, pretty much. So once you, so here's the old pictures of that, by the way. So yeah, so this is the pictures here. It's the same pictures. And so we're focusing on this yellow node. So in the first aggregate, right, you update it, and it's gonna, this yellow node is gonna update from the three neighboring nodes. So this node, and this node are blue nodes. Once you aggregate the second time, so the first time is called message passing. The first message passing, you aggregate it, and you get this information from these three nodes. And the second message passing from this green node, so this green node right here, you're gonna get information from this, it's blue node, you get information from this green node right here, and you don't get information from this yellow node anymore, mainly because this one is directed, right? So directed edge, you can't go backward. And then for this green node, sorry, blue node, this is this blue node over here. And for the second message passing of the second aggregate, you can see it take one yellow node and one blue node. So this node over here, it take one blue node, one yellow node. Same over here. This node is going to be this node, and it's going to take one yellow node and one blue node over here. Same one yellow node and one blue node. And this thing's called neighborhood hops. And so this is so that's how that's roughly how it works. This is gonna be the math side of it. So you have
Okay.
this, yes.
Sorry, can I stop right there? I'll go back. Okay, there, right there. Okay. So if I understand this properly, what you have is at the third layer. You have those two copies because the nodes are undirected, and so you can go back.
Hmm.
Um, but that one is it's caught, and so it can go to the green. The blue can't
Yes.
go back to the yellow. Okay,
Hmm.
awesome. Okay.
Yeah.
So
And
this is
then
like mapping out like how it would look if it was like a if it was a linear layer or hidden layer.
yeah, so this is like I recreate this into like the neural networks kind of. Yeah.
Yeah. Yeah, that makes sense. All right, that
Yeah.
was it.
So this is the math side of it. So you dive into more math. So this is so we only focus on one of the nodes. So this is a graph. Again, this is called node. This is called edge. And then here, we're only focusing on one node, so this node specifically. And then so this is the node in the next time step. So we're going to update this node. So this is the node in the future. And let's see, this is, hold on, do we have anything new here? I think I have anything new here. Anyways, so this is a function. This is a learnable function. So it's gonna get updated. It's just like weights and biases. It's gonna get updated so that the whole function fit more better. And the reason for this function to be here is just because of the nonlinearity. So this is a linear combination, this is a linear combination, but it is not a linear function. The data may not be linear. So there's this function, this learnable function here to make it nonlinear, but also it can update the function to make this whole thing learn. And then inside the function, the input of the function, we're gonna have h of I, t, and then w. The W here is just the weight. So we're going to update the weight, and that's how the network's going to learn. Then the second thing we're focusing on is, let's see, I don't really remember this. See, let's go back to this. This is the weight, and then HIT is the surrounding, actually, wait. Oh yeah, this one is the itself, but in the current time step. So we're still focusing on this one. We're gonna take some weight of the node itself for the next time step. So for the future node, we're gonna take some part of the original node. So that's the node itself. And then this over here is for the neighboring node. So we have U here again. This is a weight, and it's gonna get updated. And so that the network's gonna learn. And then we have over here this sigma and I over Cij. Cij, 1 over Cij is not so important. This one is just for normalization. But we have this one. This one is for aggregation functions, aggregation. And then was the reason why we call it aggregation function is because it's combining, by definition, like combining the neighboring nodes. So this sum is for the neighboring nodes of the node we're interested in. And then also another one is that is permutation invariant. And this is very important property of the aggregation function. And what do you mean by permutation invariant, right? It means that the order doesn't matter. And that's one of the point of graph neural networks compared to deep neural networks. So if you, it's the graph, right? So if you flip it, let's say upside down, it's still the same thing. So the order doesn't really matter. If you flip it either way, like if you rotate 90 degree, it doesn't really matter because it's a graph and you can just rotate or flip it. It doesn't change the properties of the graph and the nodes and the link itself. And then wait, oh okay, that's it. And then h of t of j, this is just a neighboring node, and that's mainly the map. And you just keep updating the map to get the next time step. You keep doing that. This is a more like numerically answer, and that's it. That's all I have
Hold
for
on.
today.
Okay.
Yeah.
Okay, go back. I have a question. Okay, what does U represent?
U is the weight. You can update the weight to like learn.
Okay,
Is
then what is CJI?
she which one? This one?
Yes.
This one is to normalization.
Okay.
Yeah.
Okay, I think I understand. All right. Yeah. All right. Thanks.
I have some questions. Like,
Yes.
what's inside each node? Like, are they like activation function, or do they still have activation function or stuff, new stuff?
Yeah, so inside
The
is the node is like it's called embedding. So it's like a list of like numerical values.
Okay, and are those like parameters for a function, or are they like what? Are they like the actual data itself,
Yeah,
or
they're the actual data itself. Yeah. So you can like convert the data into a numerical value, and then you can
so
input
you're
it here.
so when we say that we are changing the weight, are we changing the data itself, like in the process?
Uh, I don't think so. So this is the node itself. This is the vector inside the node.
Yeah.
The weight is separate.
Okay.
Yeah.
And the weight is applied to no, but and it change like HIT+1, the next node, it will change to something else. So
Mhm.
initially it starts like with the data, right? And then changes the data into
Yeah. Uh-huh. Yeah. Then
something
it's
else.
yeah, it's gonna change the node itself. Yeah. Uh-huh.
Okay, so eventually the data, I mean inside each node, is no longer just it's the data that you want, I guess.
Yeah.
Is that
Uh-huh. It's gonna change. Yeah.
okay? And I also have another question. Like I don't know if you said it already, but how do you guys? I mean, the how do they define like which edge goes to which, and where when is it like just one sided arrow or?
I think you can define that kind of. Yeah.
But that seems like a lot of work to do, and I don't
Oh
even
yeah,
know what
true.
to put inside each node, right?
Yeah. Oh yeah, true.
Unless it's
I don't know that.
wait, weren't there something called connectivity matrices or something like that, where you can multiply the vector of a node and it will tell you like the other node that it's attached to or something?
Maybe I don't go that deep into it.
Okay, you'll probably come across them.
an aggregate is like iteration. No, it's like each step of the no, it's each aggregate like a new step because it updates the node, right?
Yes. Yeah, it's
And
accurate. Yeah.
you're not updating all the nodes at the same time. You're updating like neighboring nodes and then back to its own nodes, like something
Yes.
like that.
Yeah.
All
And like
right.
all of them are doing that at the same time, by the way. So it's not just this node, but like all the node are doing this step too.
Yeah.
But yeah.
See, and this is only hmm, this is many. Can you show like the examples again? Like I want to see how they're applied.
Which one? This one?
Like the map one and the chemical chemical formula stuff. Like
Chemical formula. Like
yeah,
this one?
like their applications.
Uh-huh.
Yeah. Can you explain a little bit about this again? Like
Oh yeah.
what would be in like is the node gonna be the similar formula like same structure as those carbon fibers and each carbon and the data will be like carbon inside or whatever.
I think the node's gonna be like carbon, and like inside the node you can have, I guess, property of the node. And then like the link gonna be the bond, either like pi bond or sigma bond. And then so this one, what they guess is they guess the whole structure of it.
Yeah, that would that actually kind of makes sense, but
Mhm.
I'm not sure what they're putting inside the carbon though. What kind of vector or data
I
they'll
mean, you can
put to
have like
represent it.
density and other things, molecular weight density and
Yeah, I
even
see.
temperature, I guess. Yeah.
That makes sense. How about the map one? Like next slide. You have like a
Next one. This one.
yeah.
Uh, Actually, I'm not
What
sure.
are they predicting with this, by the way?
I mean, I put this one just because as long as you have a map data, you can pretty much convert it into like graph neural networks.
Yeah.
So that's pretty helpful. Yeah.
So graph neural network is still like image based, and
Yeah,
then
image based.
and you have to actually. And I feel like those nodes or the edges, like how you define the edges, is gonna be depending on how the actual image look like.
Yeah, I guess, yeah.
Because right
But
now all the examples they all have like actual links and stuff.
but I
What's
think
it?
like if you can like make two like intersection one node, then you keep doing that, and then you can have like connect the intersection by the
Yeah,
links, right? Maybe.
yeah. So there's actual physical image part of it that's requires those links.
Yeah,
Okay.
maybe.
Yeah, I have no more questions for now.
Yeah, that's a good one, good new one to look at, I think.
All right, I have one last question. How do
Yes.
we so I understand how we can use edges as the functions to predict a node from different nodes. How do we predict the value of a new edge from given nodes? Like does it require
Like this
updating
one.
the functions or what?
Sure, that's a good idea. I'm not sure, but
Okay.
like
Because that
just
was one
from
thing because that
yeah,
really
just
confused me when I was looking at it.
yeah, yeah, I guess, yeah. Like I guess well from this like what they say next Netflix video, I guess this gonna be in like the like YouTube or video recommendation system.
Hmm.
And if that's the case, I think this is gonna be a good figure for that. They're gonna make ranking. And I don't know. I don't exactly know how it works.
I'll have to look into it, I guess.
Yeah.
Okay.
Yeah, that's it. No.
That was a good presentation.
Yeah, thank you.